Tutorial number 6, Applications. Quasi-spherical orbits offer a model for dynamic three-dimensional physical phenomena. We have seen some of the results of the QSO model applied to mathematics. Now let's take a look at 5 applications in physics. Application number 1, the outermost electron cloud of the nitrogen molecule. This is a tomographic image, or CT scan, of the outer electron cloud of the nitrogen molecule. Red and blue represent opposite orientations of oscillations of the particle's waveform. The projection of QSO 1:1 on the XZ plane is an 8 curve. The 8 curve is also called the lemniscate of Gerono. The 8 curve is rotated around the z-axis, and a surface of revolution is created. The surface is rotated such that its major axis lies along the y-axis. The image of the outer electron cloud of the N2 molecule is pasted onto the XZ plane. The view along the y-axis. The surface of revolution is rotated slowly back and forth, eclipsing the tomographic image. The tight fit of the surface of revolution to the two-dimensional data suggests that the structure of the outermost electron cloud of nitrogen may be described by a projection of QSO 1:1. Application number 2, spherical photon orbits around a Kerr black hole. TO 2008 describes several special case photon orbits around a Kerr black hole. One of these resembles QSO monopole 1:2, the baseball scene. So is this a special case photon orbit? Application number 3, the strange behavior of the electron. In 1984, astronomer Paul Davies wrote, "The elementary act of rotation produces an astonishing result. If an electron is passed through a specially shaped magnetic field, its axis of spin can be progressively tipped. Eventually, the axis can be rolled right around through 360 degrees. Naturally, we would expect, on the basis of common sense, that the electron is now restored to its original configuration. Not so. If the rotated electron's properties are compared with those of an electron left undisturbed, they differ conspicuously. To restore the rotated electron, it is necessary to turn its spin axis through a further 360 degrees, making 2 complete revolutions in all. There is then no discernible difference between a rotated and an unrotated electron." Davies proposed a double wire ring model to explain the double rotation needed to return the electron to its initial state. The figure shows a bead on a double loop of wire. When the bead is rotated 360 degrees around the wire, it does not return to its original position. An additional 360 degrees is necessary for the bead to return to its origin. The QSO model suggests that the double rotation of the electron may be nothing more than rotation around a very flat monopole QSO 1:1. Application number 4, the Hippopede of Eudoxus. In the 4th century BC, Greek astronomers had a problem. They had noticed that a handful of the astral lights that filled the night sky moved or wandered across the backdrop of fixed lights. The accepted explanation was that the moving lights were carried on crystal spheres in perfect circles around the Earth. What troubled the sky gazers was the fact that sometimes the wanderers seemed to reverse their motion. From time to time, the lights were distinctly seen to go backward in their heavenly meanderings, only to soon reverse themselves and again resume their customary movement. In the heavens, where all things were perfect, this was clearly unacceptable. Eudoxus of Cnidus, 408 to 355 BC, attempted to explain the motion of the wandering lights with an ingenious scheme involving dual crystal spheres. One sphere, he said, rotated on an axis which passed through the center of the Earth. A second sphere was identical to and concentric with the first, but the axis of the second sphere was determined by 2 points on the first sphere and rotated with it. If the spheres then rotate with equal but opposite angular velocities, a light on the second sphere will describe the figure 8. Because it resembles a horse fetter, the curve is called the Hippopede of Eudoxus. A slightly modified monopole 1-to-1 makes the Hippopede. The curve is still created by the simultaneous rotation of the point on 2 axes. Application number 5, the Analemma. Sometimes called the equation of time, the Analemma is inscribed on globes and sundials to indicate the sun's declination for every day of the year. To take a picture of the Analemma, you expose the film at the same time, typically local noon, at regular intervals for a year. The Analemma is created by the simultaneous rotation of the Earth on 2 axes, the very definition of a QSO. We close with a stunning photograph of the Analemma by the modern Greek astronomer Anthony Iomamitys. The 44 solar images in Iomamitys' picture suggest that he exposed the film weekly with a few gaps.